Good afternoon. We're going to start our 7th week of lessons on page 257, and it's 15.5 in your textbook. Today we're going to be talking about acids and bases a little bit more, and specifically about pH. So pH is a scale that is used to relate how acidic or how basic something is. And I don't know if you've ever heard, things like, your water is neutral, it's not acid or base, and it has a pH of 7. So it sits in the middle, not number-wise, but in the middle of the scale as far as what's neutral. And we'll talk a little bit more on that as I get a little bit later into the lesson. So we're going to talk a little bit about how the pH scale is derived, how it's used, and we'll go into that. So when we talk about water, we almost always think of water as H2O. And if you have distilled water in a jug, it's pretty much H2O. But in reality, sometimes water will ionize itself. And so if we take, on the bottom of page 257 there, you can see that if I take an H2O liquid plus an H2O liquid, and then you can see the arrows going back and forth, so it kind of swaps back and forth with what it's doing there, that you're going to get some hydronium atom, or some hydronium molecule ions with an H3O with a plus, and you're going to get an equal number of OH minuses. So one of those hydrogens will shift over, and you'll get this situation where you will have hydronium and an OH. And one's a positive and one's a negative. Now, this doesn't happen very often. It's very rare in the water. I mean, in a gallon of water, you will have some of that happening, but it's still considered, to the billions of molecules that are in there, it's a fairly small number of them that are doing that. And the hydronium molecule ion, the H3O plus, is the Bromstead-Lowry acid, and the OH minus is the Bromstead-Lowry base. And there's one of each in there. Every time that happens, when the water breaks apart and creates an ion, there's a positive and a negative at the exact same time. And that doesn't unbalance the water, because there's a positive and negative, they kind of cancel each other, but they're still floating around in there at that level. Now, the amount of this ionization that's taking place is fairly small. You're going to get one molecule that will do that out of about 550 million H2O molecules. So 550 million molecules, and one of them will be doing this ionization, and then it'll swap back, and another one will be doing it. But you'll get one for about every 550 million molecules, so that's very small number. This makes it a concentration of 1 times 10 to the minus 7th moles. So I'm going to write that up here on the board. 1.00 times 10 to the minus 7th moles. So that's the concentration of what's, so 1 out of every 10 to the minus 7th is going to be this ionization state. Now, so you're going to have, whenever you have this, you're going to have 1 out of every 10 to the minus 7th H3O hydronium ion, and you're gonna have 1 times 10 to the minus 7 OH hydroxide ion, and so they'll be 10 to the minus 7th as well. And so when you take those two together, the total of them together floating around in there is there's going to be 10 to the minus 14th, because you're going to have 10 to the minus 7th H3O plus, and you're going to have 10 to the minus 7th moles of OH minus. So the total of these ions together will be 10 to the minus 14th moles of ionic particles floating around in your solution. Now, this is so rare here again that it's pretty much pure H2O. I mean, at those low levels, there's very little that's going on there. Now, so if for some reason we had just a little bit more of the H3O than the OH, this would not be the natural situation for water, but just for discussion's sake, if we had a little bit more of the H3O than the OH, then the solution would be slightly acidic. Or if we had just a little bit more of the OH minus in solution, then it would be a base, a basic solution. So the way we rate these is on the pH scale, and we're going to talk a little bit about how that pH scale comes into play. But before we do that, I want you to look on the top of page 2. Well, first look on the bottom of page 258. It shows some neutral and then an acid and a basic solution, where if the same number of the plus hydrogens that are connected with the hydronium and the OH, then it's neutral. If you have more of the plus H, you're going to be acidic. If you're going to have more of the OH, you're going to be basic. So let's look at the top of page 258 at table 15.8. It says approximate pH of some common materials. So the first one that's listed is a 0.1 molar solution of hydrochloric acid, and that has a pH level of 1. So when here again, if you have water at 7, that's neutral. If it goes less than 7, that shifts into the acidic levels, and the lower the number gets, the more acidic it is. Or the higher it gets getting towards 7, the less acidic it is, and the more neutral it becomes. And then if the number goes above 7, like an 8 or a 9 or a 13 or a 30, because it can go really, really high, then the more basic it becomes, and the more you can have some very, very caustic bases, and you can have some very, very acidic bases that get really low. They can go less than the 1.0. You could have a point something on an extremely, extremely aggressive acid where there was a whole lot more of those hydronium molecules floating around in there with the plus H's all over. So this pH scale is logarithmic. Now, as a review of what logarithms are and how that plays in, I'm sure you've dealt with them in your math classes somewhat, but a logarithm, the natural logarithm, is a base 10. So so in the base 10 scale, we'll go over it a little bit here in your book to make sure that I don't mix it all up, but if you have, it's powers of 10. So 1,000 1000 is equal to the log of 1000. So if you take the log of 1000, then that's going to equal 3, because there's 3 positions. If it was a million, this would be this log of 6. If it was 10, then it would be 1. So, and 100 would be the log of 100 would be 2. And so you can see that this logarithmic scale, as it plays out, is kind of like this. So the 7 is a log position, and we'll explain here in just a second how that works. So logarithms give you the ability to express a large numbers of something in lower numbers, like 1000 you can say is 3, and the log of 1000 is 3. So if you were looking on a logarithm scale, you would have 1 to 10, and then you'd have 10 to 100, but this distance on the logarithmic scale would be the exact same. So I'll draw it out here a little bit. So starting right here, I'm just going to do some fairly equal space as close as I can. And if this is 10, then this would be 100, and this one would be 1000. And the way the logarithmic scale works is that 5 is not right in the middle here. 5 is going to be about right here. 50 is going to be about right here. 60 is going to be, not 60, sorry. 500 would be about right there. So it compresses as it goes this way. And then by the time you get to here, it compresses, and then it compresses because there's between 100 and 1000. All the numbers between 100 and 1000 are in that position. And you can have numbers that are different than just, like this is the 1, 2, 3, but you could have something in the middle, like the next one here would be 10,000 or 4, but we could have an expression of what 5,000 is, and 5,000 would be 3.669. So it's 3, so 5,000 would be about right in here. Is 3.6, make sure I'm giving that right. Yeah, 3.699, sorry. 3.699. Now, years ago, logarithms were on charts. You would have a book of logarithms, and when you didn't have big calculators and things like that, people like Newton and a lot of those early, very famous, very brilliant scientists in that would use logarithms for dealing with really large numbers, because you can multiply extremely large numbers by just doing addition. So it's really, really cool. And there's a few things there's a lot of other tricks with logarithms. And the old magical pre-calculators was a slide rule, and the slide rule was based on logarithmic scales so that you could do addition and get multiplication and things like that. So it's with the slide rule. So they're really fun to play around with. So anyway, that's the way this pH scale works. Now, if you take, the way the pH scale works is we take the number of hydronium atoms, or molecules, sorry. So we take the number of hydronium molecules, which which we said with regular water was 1 times 10 to the minus 7. And we take the negative log of that. And the negative log of this is, well, first of all, let me go to this. This is 1,000. That is the same, the log of that is 3. But another way of writing this is 1 times 10 to the third. You can see that the log is the same as this exponent. So this is the same. So what we can do is the log of this would be minus 7. But for a pH scale, we use the minus log. So we would take this number and we would take the minus log of that, and that would give us 7. Because this would be a minus 7, and when we take a minus with a minus, you get a positive. So water has a pH of 7. And now there is the pH is the H. It's written like this. It's a little P and a big H. It's talking about the amount of hydrogen. Now there is a pOH scale as well, but it's very closely related to pH, but I don't know of any things that use this, because when you do the pH, you can express how much base it has or how much the other. But this is a proper scale. It's based off of the OH, and it's very similar in the way it's worked. So let's do a little bit of the math here that's on page, the bottom of page 258 and goes over onto the top of page 259. The first one says that we have 6.25 times 10 to the minus 8 is our amount of the H3O positive, or the hydronium atoms. Now, this is something that will require a calculator. I mentioned that in the old days that logs were used with charts. It's pretty hard to even find those charts unless you've got a special book anymore. Your calculator is by far the fastest. It's going to have a button on there that's going to say LOG. So if you hit 1,000 and hit LOG, it's going to take the log of 1,000. So if you take 6.25 times 10 to the minus 8, now remember, this is not a times button in this application. This is an expression of a scientific notation to express where the position of the decimal is. So it's not 6.2 times button, it's the exponent button, which on your calculators, it's been quite a while since we've used them, but it's probably going to have a EE button for an exponent button, or an EXP button, or some calculators have an ENG button that'll do it. But what it'll do is, as soon as you type it in, you will see that it will have the number that you put in, 6.2, you hit the EE or whatever button it happens to be, and then you type in the minus 8 that this would be. That is an operation that creates a scientific number. Do not hit the times button, you hit the EE to get that. Okay, so you put in 6.25 times 10 to the minus 8, and then you take the log of it, you hit the log button, and it's going to come out with a minus number, which I don't have my calculator with me right now, but it's minus 7.24. And when you take a minus to a minus, That means that it's 7.204 is the pH of that, which means that technically it's slightly basic because it's a little higher than 7. You probably wouldn't hardly even notice that it was basic at that level, but it would be slightly basic. Now, the next one is the OH. Now, when you're given an OH, we have to compare it to the pH scale. That's what we're doing, and so you have to do the division that's in there, where you take the constant of minus. So you can see the minus, the 1 times 10 to the minus 14th over the OH, and that's going to give you the calculation. It gives you 3.13 times 10 to the minus 12th molar, and then when you run that against the log, it's going to give you 11.504. So that is very basic. It's going to be quite a bit more basic than water at 7. And then the last one on here was a 0.0010 molar hydrochloric acid. And when you run that through and you put that in there, the 0.001 molar, then you're going to get and you take the log of that and take the minus of what your answer is, you will get a 3. So that has a lower number than 7, and so that's acidic. Now I want to go back over to the table on 258 and talk about a few more of those. So we mentioned the hydrochloric acid was 1, had a pH of 1. Gastric juice, that's what's in your stomach, 1.7. That's very, very acidic. In fact, that's why if you get things like ulcers that eat through the stomach lining, because you have a mucus lining in the stomach that protects the stomach from this, and it's constantly being regenerated, but it protects your stomach from this acids that are in there, because they're very potent acids in your stomach. A lemon juice is 2.3. Vinegar's 2.9. Soft drinks have an acid level of about 3. Orange juice 3.5. Bananas 4.6. Now we go, coffee has an acidity of 5, so that still has an acid level. Rainwater is 6.2. Mostly because rainwater picks up some of the ions out of the atmosphere and stuff like that. Blood is 7.4, slightly more basic than neutral water. An egg white is 7.8, seawater is 8.5, so it's even more basic with all the ions that are floating around in there. There's a lot of negative ions and stuff that kind of work with that. And then you've got 0.1 molar sodium hydroxide, and that has a 13. So it's very much on the base scale. So here again, once, just to kind of go over this again, the lower the number is, the more acidic it is. And neutral is at 7. And the higher the number, the more basic it is, and if it's a number larger than 7, then that would be a base. And I think that's where we will end today, and I will see you on the next lesson.